All right, let's take a look at page 528 in the notes as we start day 52 in our workbook. So this is talking about the fundamental theorem of calculus and how it applies to particle motion. Remember, particle motion is when we're talking about some sort of particle that's moving in a one-dimensional space. So it's moving left or right along the number line. Two-dimensional space is a lot harder to deal with. You can talk about that in your physics class if you ever get there. All right, and remember, we've got three basic functions. We've got v of t, which talks about your velocity over time. We've got, they describe it here as P for your position. Another thing that you'll see probably more often is x of t, talking about its position on the x-axis as a function of time. And then the third is acceleration, which is a as a function of t. And remember that the way these are set up and why Sir Isaac Newton talked about created calculus so he could talk about physics problems is that velocity is the derivative of position and acceleration is the derivative of velocity, which makes sense, right? If you're accelerating your car, your speed is changing over time, and your speed is talking about how your position changes over time. All right. So three things to always keep in mind when you're dealing with these problems. The first is that the definite integral from a to b of velocity over time is equal to the difference between the positions at those two times, where v of t represents the velocity and p of t, or as I say, x of t, represents the position. This is just the fundamental theorem of calculus because position is an antiderivative of velocity. The next two things are talking about what we talked about in the last video, that if we're taking the integral of velocity, taking a definite integral of velocity, we're talking about the difference between two positions at the beginning and end, and that's the net distance that the particle travels on the integral from time equals a to time equals b. All right. If the velocity is always greater than 0 on the interval, then it also represents the total distance. Okay, so velocity greater than 0 means the thing is always moving to the right. So if the particle is always moving to the right, then obviously the total distance that it travels is going to be the same as the net distance it travels because it never doubles back. But if we want to talk about the total distance, remember we talked in the last distance about how total distance is different from net distance. We can do that by taking the definite integral of the absolute value of velocity. All right, so if you've got a velocity graph that looks like this, velocity over time, and so this is talking about how it's moving to the right for a while and then it slows down and then it becomes negative. So we're talking about it moving left for a while and then coming back to rest. If we want to talk about the total distance, what we're going to do is we're going to just take our entire curve and make it positive. So this is the absolute value of v as a function of t, whereas this was the original velocity as approach to t. All right, and so doing the absolute value is going to measure the total distance whether or not the velocity is always greater than 0. To be safe, whenever a problem, especially on the AP exam, asks you to find total distance, you should be thinking about using this formula, because something moving to the right and then moving back to the left, if they ask about total distance, we want to consider those as adding to each other and not canceling each other out. All right, so the velocity of a particle that's moving along, now why don't we do this in the next video? All right, so we will start looking at how we can solve word problems involving linear motion by using the fundamental theorem of calculus and these definitions.